Welcome to Xamarin University and AND230, Google Maps. In this class, we're going to explore how to add maps into our Android applications. This is an introduction to mapping with Android, and we have a lot to talk about. A lot of it is actually setup related. We'll start by looking at the options you have when incorporating mapping support into your application. Now, there are different ways to incorporate map support into an Android application. So we're going to look at a specific approach that involves using the Google Play services. And we'll also talk about how we can test mapping support on an emulator. Now, there are a variety of reasons why you might consider adding mapping support into your application. It can enhance and it can integrate information, making your application much more useful and complete, particularly any application that needs to deal with locality or geographically bounded, interesting places around the device. Now, the easiest way to add mapping support is to just activate any built-in mapping application. And this can be done using the geo MIME type with the action view intent. The URI string takes the latitude and longitude, and then when the activity is started, it will launch whatever the registered maps application is, and then position the view at the specified coordinate. One note on this approach, though: you must first verify that there is a registered application to handle this URI. This can be done through the resolve activity method on the intent. This will return true or false if there's a valid system registered activity that can process this URI. There are other URI formats available to launch Street View, map searching, and turn-by-turn directions as well. Now, this external launching approach is perfectly fine if the location information isn't really central to your application. So for example, if you're displaying the address of a storefront and the user wants to see it on a map, they could tap the address and spin up whatever the Maps app is automatically, versus a more primitive kind of copy-paste approach. However, sometimes we need the mapping information to be a bit more central to our application, and we'll need to turn to an API for this. Now, unlike iOS, Android doesn't have a standard mapping API that's available on every single Android device. Here you can see some of the choices that you have available to you. Most of these libraries are bound right into your application package, and then they retrieve the GeoMap tile data from web services. Most of these are very comparable in terms of features. The real difference is in the quality of the mapping data and the types of layers that you can provide. Satellite versus topographical, for example. We don't have time to cover them all, but you can easily look each one up and compare them against your own requirements. We're going to focus on Google Maps, which is the most common API used for Android apps because it comes from the manufacturer. However, before we can jump into the API, we have some prerequisites. It turns out that the Google APIs have a pretty significant setup requirement for development and a runtime requirement on the device. So let's talk about that first. Now, Google has a variety of extra APIs that you can use in your Android applications. These APIs ship in extra APK libraries, which can be linked into your application and must also be installed on the physical devices that your application runs on. These APIs include Google Maps, which we're going to focus on in this class, and location support, which is the next class, our AND231 class. The Google Play services have a bunch of other services as well: Google Wallet, Google Drive, and more. Keep these other APIs in mind if you want to integrate more closely into Google's server infrastructure. When you're using Maps, it's best to test on a physical device. If you have one with the Google apps, like Google Maps, installed, then you should use that for the exercises in this class. If you don't, then you'll need to configure an emulator. Google has pre-created Google APIs and Google Play emulator images that you can use to test your apps. These images are installed from the SDK Manager, as you can see here in the slide. Make sure to download the x86 version and use either the Intel Haxum kernel extensions or the Hyper-V extensions to improve the performance. When you run this image, it will include the standard Google apps, things like Google Maps. This is an easy way to see if the APIs are available before trying your application. The appropriate Google emulator images include the required libraries that your app will use, but we also need the binding library to access that API from our C# code. This is provided through a NuGet package named Google Play Services Maps. The mapping services that we're going to use are provided through the Google Maps Android API v2 that's part of the Google Play Services library. As I discussed a moment ago, the device must have the Google Play Services installed. Additionally, the device must support OpenGL ES2, as Google Maps uses that for drawing the map tile vectors. The Google Play Services are not installed on every Android device though. It's a licensed API, and not every manufacturer chooses to license and pay for the API. If you attempt to run an application that uses the APIs on a device where it's not supported, you'll get an error prompt and the application will not be allowed to execute. As you can see in this code here, you can defensively program against this behavior and provide an error prompt that is much more user-friendly. There are some methods exposed on the Google API availability.instance singleton that makes this task fairly easy to do. So in this example, we check for the play services at runtime, and then we use the library to display an alert dialog along with a blank view, which we can close when the alert's dismissed. This gives our app the control over the error and the closing of the app, which is preferred. Now that we've got the setup requirements out of the way, let's look at how to configure our application to use the Google Maps API. And we have several steps that we need to do to our application. We'll need to create an API key, register the application with Google Maps API, and set our permissions. First, we need to create and register an API key for our application so that the Google services know about our apps. For some fee-based map implementations, you might have to set up an agreement with Google to pay for using the service, but the Android API is generally free for unlimited free usage, even in paid apps. Next, we have to set some specific permissions in the Android manifest that will allow us to retrieve the mapping tiles. And then finally, we'll have to add the NuGet package to our application, which will invoke the APIs and display the resulting map information in our application. So in order to access Google servers, the first thing you'll need is a Google Maps API key for your application. Without this, the map servers won't respond to your application and the map will remain empty. Google uniquely identifies your application through a couple of pieces of information. First, it uses the fingerprint associated with the signing keystore of the application. So here's the big picture. When you build your Android application, the build tools take your generated APK and sign it with the keystore. This creates a signed application which can then be identified by Google and sold on the Play Store or installed on a retail device. The keystore itself is actually just a certificate file on your file system. When you create a debug version of your application, the system uses a single debug keystore, which is shared for all apps by default. You can change this behavior on the Android Package Signing tab in the Build options. For release builds, you will typically create your own private keystore, possibly unique to the application, although there are some advantages to sharing the keystore across different applications that you publish. The primary purpose of the keystore, at least for your Android application, is to identify the app and the author prior to allowing the application to be installed onto a device or to be published in any of the Android stores. The certificate does not need to be signed by a certificate authority. In fact, most apps use self-signed certificates. However, the private key is kept by the developer, and it must be the same each time the app is versioned, or the Android store won't recognize the app submission as the same application. And it turns out that the Google Play services rely on this certificate as well. A portion of the certificate, called the fingerprint, is registered with the Google Play Services Developer Console, along with the package ID, and is used to generate a unique application key, which must be added into your application manifest. By default, the keystore that is used to sign debug versions of a Xamarin Android application can be found at the locations on the screen. However, it's important to remember that the location can be changed, and when you create a release build for publishing, you'll use a different keystore that you must create. The tooling in Visual Studio will walk you through this process. Both the debug and the release keystore fingerprints must be registered with the API console so that build types can use the Google Play services. Now, information about a keystore is obtained by running the keytool command from the JDK, using the command line you see here on the slide. The key tool should be in your path, but if not, it will be in the bin folder of the JDK. Again, let me reiterate that you will need to register both the release and debug keystore fingerprints. We will only work with the debug version in this class because we aren't preparing for publishing, but once you get to that point, you will want to add that fingerprint into the console. So here's an example of retrieving the fingerprint information from the debug keystore on a Mac. Now, one quick point on this example, the debug.keystore file is created when you deploy a debug app to a device or an emulator. If you haven't done that yet, you won't have a debug keystore file yet. So if the file does not appear to be present, try deploying an app first to see that it creates the keystore file. Now, the fingerprint that we need for the Google Play API console is the SHA-1 fingerprint, highlighted here. This is a 20-byte colon-delimited value, which you'll need to copy down to register with Google. The keystore will have a set of passwords associated with it. These are assigned when you create the keystore. The default debug keystore uses the values Android for both the store password, which is used to protect the file itself, and the key password, which is the password for the private key stored within the file. And then finally, if you're using Visual Studio for Mac, there is an add-in available in the Visual Studio add-in repository, which you can add to the IDE to help you locate the fingerprint automatically. Just use the System menu and then the Add-in Manager to open the manager. Look under Mobile Development and install the Android Signature tool. And then a new menu option, Keystore Signature Tool, will be available under the Tools menu to open the tool. And you can point that at your custom keystore or use the default debug keystore. This makes it a lot easier to find your SHA-1 signature, which is exactly what we're going to do right now. So we're going to start with our very first exercise. Open up exercise 1 from the worksheet that you downloaded from the Xamarin University site that accompanies this lab. Go through that exercise, find your SHA-1 fingerprint, pause this video, and come back when you're complete with that. Once you have the SHA-1 fingerprint, it's time to register the application. You'll go to console.developers.google.com and either create a new project or select an existing one that you've already created and turn on support for the Google Maps Android API in the APIs and Services library section within the Maps category, as you see here. Then we'll need to add our application credentials. This is where we will register the SHA-1 fingerprint in the package ID. It is possible to create unrestricted API keys. These keys don't require the SHA-1 fingerprint and they'll not be tightly coupled to your application. That might sound tempting as it reduces the number of required steps, but keep in mind that Google will eventually charge you if you generate enough traffic to the API. An unrestricted API key is substantially easier to abuse and can be used outside of your application. So it's recommended to create unique keys for each published application. Give the new API key a name and then restrict it to Android apps with our fingerprint and package ID. Google allows about 5 key and package name pairs to be tied to a single API key. If any other developers need to use this same API key, you'll either need to share your debug keystore with them or add their SHA-1 as additional key restrictions. And make sure that the package ID that you add here matches the package name in the manifest exactly. This will create an API key. This is the critical piece of information we need to embed in our application. Copy this value down and add it to your Android manifest. There's 2 ways to do this. You can hand edit the XML file and add in the metadata tags into the application tag, and that's ultimately what we really need. However, that's a little bit painful to manage when you switch between release and debug builds because the key could change if you register them separately. An alternative way to do this is to use the metadata attribute tag in a source file. This should be applied at the assembly level, as you see here, and will insert the proper XML at build time. Just paste the copied key right from the console into the tag, and you're all set. Finally, you'll need to work with Android permissions. There are several permissions involved with Google Maps. At a minimum, your app will need 2 permissions in order to display a map. We'll need access network state. Maps must be able to check if it can download the map tiles. We'll need the internet permission, because internet access is necessary to download the map tiles and communicate with the Google Play servers for API access. Explicitly adding these 2 permissions is optional, since the Google Maps package will automatically merge them into our app's manifest at build time, but it can help others understand your app when they're added to the manifest directly as well. If you want to work with your app user's current location, you'll need to add 2 additional location permissions. There's access course location and access find location. These permissions will allow the Google Map to display the location of the device on the map. Now, setting the permissions using the GUI editor of Visual Studio will automatically add the permissions to the application manifest. So here's an example Android manifest in source form after those changes. You can also edit the manifest directly. With the original install time permissions, Android would ask for all of the possible permissions an app could use when the app was installed by the user. Apps could have been asking for very extensive permissions just by convincing the user to install the app. An app could access confidential data without the user understanding the risk. Android has evolved the permission system to increase security for the user since version 6, classifying permissions as normal and dangerous. Normal permissions, like network access, are granted automatically. Dangerous permissions, like access to the user's contacts, photos, and location, require the user explicitly granting that permission when the app is running. The first time an app has Android request a permission from the user, it will be a plain deny or allow dialog for each permission requested. If the user chooses to deny the first request and your app needs to ask for that permission again, the dialog will now offer an option to prevent your app from asking again. This allows users to keep a persistent app from interrupting them again and again, but it also means that permission cannot be granted without the user granting them to your app directly in the Android Settings app. Users have granular control over these permissions as well. They can revoke or grant individual permissions at any time from the Android Settings app. As a developer, this new permissions process means we have to navigate a few possible situations. If we've already been given permission previously, we can simply use it. Because the user could revoke our permission manually, we need to keep this check in place for any method requiring a dangerous permission. If we don't have permission, we check if Android thinks we should show some sort of explanation for our permission. If we've been denied the permission previously, we might want to explain why we need the permission. Alternatively, if the permission you are requesting is for something non-obvious, you might show the explanation UI even for the first time you ask the user to grant it. For example, a camera app may want to show a dialog explaining that it can geotag the user's photos if they allow the app to access their location. Now, whether we showed an explanation or not, we still need to have Android ask the user for permission. From there, the user will give their response to Android, and we handle that response in an activity callback method. So as a developer, how do we work with this user-focused permissions model? Well, first, this new approach is in addition to the manifest permissions. Keep those manifest additions set, even if you don't support older Android versions. When your app needs to make use of an Android feature that requires user permission, whether that's on the first launch for an app that requires it at all times, or when they click a button to fire something off, we call a series of permissions methods before handling a resulting result callback. First, you call check self-permission on the desired permissions. Once your user has granted permission, this will be the typical execution path. If you don't have all the necessary permissions, you call should show request permission rationale to see if Android is suggesting that you explain why the permissions are necessary before asking the user again. If you asked previously and the user checked don't ask again, you want to display some custom UI to convince them to allow the permission when Android asks again. If we decide we actually need to request the permissions, we call request permissions. When we do ask Android to request the desired permissions, we mark our request with a custom request code unique to that request. This request code should be distinct for any request that requires different handling of the provided results. So a simple example of this would be requesting camera permissions for one button tap and location permissions for a different button tap. When Android gets a response from the user on the permissions dialog, it will call back to your app through the onRequestPermissions result. This method could get called for any number of permissions requests in a complex app, so we need to react based on the request code that we provided Android when it asked the user. If all the permissions we requested come back as permission granted, we're free to use the APIs requiring those permissions. This can be a fairly complex process in a well-planned app. In the next exercise, we will provide most of the code for you in a helper class so that we can focus on the mapping. Also, if you end up working with permissions regularly, Xamarin and James Montemago have published a permissions plugin called plugin.permissions on NuGet to simplify consuming the permissions. Additionally, the plugin also works with iOS and UWP permissions. So let's go back to our worksheet and work on the next exercise, and we're going to make sure we go get a Google API key from the Google Maps console. Pause this video and come back when you have that API key. So now we've found out how to actually create an API key and register the application with the Google Maps API. Now that we have the setup requirements out of the way, let's look at the API itself and how to use it in our applications. We'll look at the basic classes used, how to display the mapping data, and then look at some of the options you can use to control and adjust the map controls. The Google Map class encapsulates a map. It enables features such as controlling the map type, adding graphics and markers, zooming and panning the map, and adding traffic data. The mapping APIs require either a minimum of API level 12, or you can add the v4 support library to get support classes and use the fragments and mapping APIs on down-level devices. We'll assume that you're on at least 4.4 in all of the exercises, but keep in mind that it's possible to use the support libraries and get a lot of the functionality on very old Android builds. To add the UI into your application, you'll use one of two approaches depending on how your UI is constructed, either a map view or a map fragment. The map fragment is the most common approach, and that's used when you're adding the map into your layout for an activity. You can use the entire screen, as you see here, or take up just a portion of the UI by manipulating the layout properties of the fragment. You'll add an ID to the fragment so that you can access it in your activity, and then set the class attribute to com.google.android.gms.maps.map_fragment. As you see here, that will load the component into your UI. This markup must be added into your UI directly in the XML, as there's no designer support for fragments in the Android designer today. Now in your activity, you'll use the Fragment Manager API. Pass in the ID from the XML to locate the loaded fragment. This will return the map fragment object, which we will eventually use to retrieve the Google Map itself. Now, alternatively, you can create the fragment completely in code. This could be useful if you are dynamically constructing your UI based on the device or the form factor. The other option is to use the map view object. This is an Android view that displays the map data. Its primary purpose is to be used inside a custom fragment that's defined in your application. Since fragments are not intended to be embedded into other fragments, this approach provides a simple solution. Now, because MapView is an independent view, it must be hosted properly in order to render its details. One of the main things you have to do is forward the lifecycle methods from the fragment owner down to the view. This includes the onCreate method, onResume, onDestroy, and onLowMemory. So, there are two approaches. Which one should you use? Well, generally, you should prefer map fragment. It's intended to be placed directly into your UI, and it's the simplest to use. If you're composing your UI from fragments, for example using a view pager, which works directly with fragment elements, or using fragments to compose the app structure to work on a phone and a tablet, then you would prefer the map view and forward the lifecycle methods. Both will perform the same task, and they have exactly the same API surface for working with the mapping API. Let's check that out next. The first thing you will need to do is get access to the Google Map object. This is your gateway to customizing the map and controlling the interactivity. There is a map property, but it's been deprecated because it's not available until the system properly authenticates to the Google Map services. So, the proper way to get the map instance is through the getMapAsync method. This method is not C# task-based, despite its name. It requires that you pass in an implementation of the onMapReady callback interface, which we are implementing here on the activity itself. We can then cache off the past reference in the onMapReady method and customize the map experience since the map is actually ready to be used here. Now, one interesting caveat here, which might not be obvious, the map is reloaded each time the activity is changed. For example, when the device is rotated or the app is suspended and then resumed. In these cases, the callback is invoked again to reinitialize a new Google Map instance since the activity was recreated. The new map instance will be scrolled to the same position and zoom level, but any other configuration options are not automatically restored. Also, the mapping API is UI intensive, and all the properties and methods should always be accessed on the UI thread, particularly anything that changes the visualization. So let's talk about some of the properties that you can use to customize the map experience. Google Maps supports 4 different map types: normal, satellite, hybrid, and terrain. These are set through the map type property. You can also turn on a current location marker on the map. The My Location Enabled property on the Google Map object is a Boolean that turns on a current location pointer on the map. You must have both coarse and fine location permissions in the Android manifest to use that feature. These permissions are not required if you don't intend to use the custom location marker. Enabling this feature doesn't return any data to your application. You can't determine the latitude and longitude of the user's device with this feature. It simply makes it present on the map. We'll learn how to get the current location in the next class. Finally, there's a UI settings property that determines what kind of interactions are present on the map. For example, you can turn on a compass, a current location button, and a set of zoom controls. If you're creating the map fragment in code, you can pass a Google Settings object to initialize many of these features as part of the construction. The UI Settings class also lets you control the gestures which are available. By default, all gestures are turned on, but you can turn them off in order to support a read-only map which can't be moved, zoomed, or rotated. That can be useful if you're showing a specific landmark at a specific zoom level and you don't want the user to reposition the map view. And now let's get into our next exercise. We're going to add support for Google Maps. Remember, pause this video and come back when that exercise is done. So we've now seen how to actually add the map UI into the app and configure it. Next, let's talk about adding annotations to the map in the form of visual markers. Google Maps has built-in support for adding interactive markers and overlays to the map. We're going to look at the primary feature here, which is markers. However, the map also supports adding shapes, lines, and tile overlays, all of which is covered in a separate lightning lecture that's available on our website. A marker is an image that corresponds to a specific location on a map. These are equivalent to annotations in iOS. The default marker looks a bit like a colored balloon, but as you're going to see, we can customize this in several ways. To define a marker, we'll use a class named MarkerOptions. The MarkerOptions class defines the characteristics of the marker, including where to place it, which always has to be supplied through the setPosition method. The configuration API is fluent, meaning that each method you call returns the MarkerOptions instance back to you so that you can chain your methods together. This allows you to construct the marker on a single statement. The only required property is the location of the marker. This is done through the setPosition method and is assigned to a lat-long coordinate. The method returns the same marker options back to us, so then we can chain on to the next method, which sets the marker color. The default marker color is red, but you can change it by passing a specific color constant from the Bitmap Descriptor Factory class. There are 10 fixed colors to choose from. Once the marker option has been created, you put it onto the map by calling addMarker. This returns the created marker object. There's a variety of settings you can control when you create the marker. Properties are set through the set methods. The property values themselves are all read-only. Some of the more interesting values are alpha, that's going to change the transparency, rotation will rotate the marker, and flat will flatten the marker out, and have it rotate with the map. By default, it's not affected by the map rotation. Now, if you aren't a fan of the balloon shape, you can supply your own image for the marker. This is done through static methods on the Bitmap Descriptor Factory class, which let you load an image from an asset, a file, or a resource. The image can have transparency, it can be any size, and it can be positioned to the coordinate through the anchor property, which controls the pixel in the image that's placed at the lat-long position. The anchor point is specified in the range of 0.0 to 1.0 for one axis and 0.0 to 1.0 for the other axis. 0, 0 is the top left corner of the image, and 1, 1 is the bottom right corner. The anchoring point for the image is decided by scaling and rounding the width and the height of the image against the given bounded position. So here, we're positioning the bottom right corner of the image to be on the coordinate. One thing to be aware of, the markers are not sized to the map, so they are always a fixed size regardless of the zoom level on the map. In this case, our marker image would always be 150 by 150 unless we changed it later. The marker options properties are read-only, but once you've added the marker to the map, you can use properties exposed directly on the marker instance to adjust its visual presence. For example, you might change the color to indicate some real-time state, or adjust the image based on the zoom factor to provide a marker that scales with the map. The marker overlay can also show additional details. This can be used to annotate the marker and show details about what the marker represents. This again is accessed by using the Fluent API exposed by the marker options class. We can set a title, shown in bold, and a subtitle, which is called a snippet, which is shown in a more muted font. By default, this pop-up is shown when you tap on the annotation, but you can also use the show info window method on the marker options class to display it initially on the map. There's an equivalent hide info window method as well. The marker property is info window shown can tell you if the info window is visible, and you can also adjust the position of the info window using the info window anchor method on the marker options class. We're setting it here to 0.5 and 0. However, that happens to be the default, the top center of the marker as you see in the image. As you can see here, the values you pass in are normalized to that 0 to 1 bounds, so you don't need to know the size of the marker image. Now, if you don't like the way the info window is visualized and shown on the screen, you can take over the rendering through the InfoWindow adapter interface through the setInfoWindowAdapter method. You can only assign one adapter for all markers on the map though. So here's an example of an implementation of the InfoWindowAdapter interface. The implementation has to extend the Java object since it's going to call or be called by the Java runtime. And it implements one of two methods, either getInfoWindow or getInfoContents. The getInfoWindow method is used to draw the entire pop-up, both the frame and the contents, while the getInfoContents method returns a view just for the contents of the pop-up. The system provides the border. In this example, we're inflating a layout XML file, filling it in with data from the passed in marker, and then returning it to the caller. These methods are called each time the info window is displayed, and you should only implement one of them for any given marker. When you return null from one of the methods, you tell the system to just use the default implementation. You can use this in order to customize only a select set of markers, for example, providing a view only when the marker is matched, and then returning null in all the other cases to get the default info window view. We can also interact with the markers in the info windows, as well as with the map itself. Xamarin exposes traditional .NET events on the Google Map instance to provide these interaction points. Under the covers, the map actually uses Java interfaces for notifications, and this mechanism is exposed, and it could be used if you like, but the event approach surfaced by the Xamarin framework is much more convenient and .NET-like. You'll typically wire up all of your events when you initialize the map, often in your on-map ready implementation. All of the normal event lifetime rules apply here. If the map fragment is temporary in your UI, then you want to make sure that you unsubscribe from any events when it's removed, or ensure that the handlers are in objects that have the same lifetime scope as the map UI. Don't use static handlers, for example. Now the first event is the marker click event, which is used to notify your application that a marker was tapped. The handler is passed a marker clicked event args, which can be used to identify the marker that was activated so that you can provide custom behaviors. Notice that we're using the marker.equals method test for equality. The C# double equal sign operator isn't consistent in all cases, so you should prefer this approach, or compare the auto-generated ID property of the markers for equality. One important thing you'll need to deal with is the handled flag. Once you register for the marker click event, the Google map will, by default, not perform any action when you tap a marker. This is controlled by the handled property in the event args. This is set to true by default, and it indicates that your handler has processed the click and no action is necessary from the map. You could do some work and then show the info window, for example. Alternatively, if you change the flag to false, then the map will continue the normal activity for the marker. Keep in mind that if you change certain visual properties on the marker, it's possible the info window might not be displayed, so in that case, you still might end up showing the info window through the API. But generally, the best practice is to return true only if you dealt with the marker and return false if you didn't. One other built-in behavior for markers is dragging. You can allow the user to drag a marker by tapping, holding, dragging, and then releasing. The movement is provided automatically by the component, and your code is notified through the marker drag event, which is, again, past the marker as well as the new position. You could also respond to the marker drag start and the marker drag end events if you want to monitor the entire process. You can also add logic when the user interacts with a displayed info window. In this case, the info window click event is used to notify your application that an info window has been activated. Finally, we can get notifications related to tapping on the map directly, or long clicking, where we hold our finger down for an extended period of time. These events are both passed the touch coordinate as a lat-long object. If you need more fine-tuned interactions, for example gestures like swiping or drag operations independent of the markers, you can use the lower-level motion events from the parent view and then convert the screen location into a lat-long object using the projection property, which can transform screen pixel values to and from map coordinates. We cover the touch events in our AND230 Touch and Android class. And now, let's go to our next exercise where you will work with the markers. Pause this video, work on that exercise, and then come back. We've now seen how to add and work with map markers on our map. Now that we've seen how to create and display the map, let's see how to reposition it using the built-in camera APIs. So we'll talk about how to change the camera position, either through a direct movement or through an animation. The default rendered map is performed on a two-dimensional surface, where the camera is directly above the map surface. The map allows you to control this camera position and change the location, the zoom level, the tilt, and the compass direction the camera is pointing, called the bearing. The key to the camera API is the camera position class. This is a read-only class that exposes properties for each of the changing values. You never change a camera position. Instead, you always construct a new one, possibly from an existing position. This can be done in a couple of ways. First, if you want to control all the aspects of the position, you can use the invoke builder static method. This returns a builder object, which has a fluent API where you call successive methods, each returning the same builder object to control the various aspects of the camera position. You can set the lat-long position of the camera through the target method. Coordinates are always represented as lat-long objects, with the coordinates specified as double values. You can adjust the zoom level through the zoom method. The zoom level is typically in a range from 1 to max zoom level, with 1 being the furthest away. At zoom level 1, the equator of the Earth is 256 pixels long. Each successive zoom level is magnified by a factor of 2. Keep in mind that not all tiles have high-resolution representations for every zoom level. You can adjust the compass bearing through the bearing method, which is specified in degrees clockwise from north. and the viewing angle using the tilt method. This is the angle in degrees where 0 is directly facing the Earth. Now once you've set all the values, you must call the build method to generate the read-only camera position object. We can then use this object to change the map position. The first way we can adjust the map's position is through the move camera method on the Google Map object. This takes a camera update object, which can be created directly from a given position through a factory method, as you see here. This will redraw the current map view at the given position, taking into account all of the parameters, the zoom, the tilt, the location, the bearing, and so forth. So we can create a new camera position, but often what we want to do is adjust the current position of the map. This is most easily done through a set of factory methods, which return camera update objects from a difference of the current camera position with some adjustment. A second way to move the camera is to animate it. This is done through the Animate Camera API. You can pass a camera update object to it and use a system-supplied animation, or pass an animation time in milliseconds along with an optional callback for when the animation is complete. When you animate the position, the user is treated to a sliding map where we zoom in or out and reposition the camera in a smooth fashion. There's also an API to stop the animation if you want to cancel it. Typically you would do that due to user interaction or changing the settings. Then finally, if you need to, you can monitor the position of the camera through the camera change event on the Google Map. You're passed the new camera position, which would include the coordinate, the zoom level, etc. This is useful when the map is interactive and you need to track where the user is looking so that you can look up points of interest or place custom markers on the map. We'll talk about those specific features in the next course, AND231, Locations. And let's finish up with our last exercise, and we're going to use the camera APIs and change the map viewpoint. Pause this video, come back when you're complete. So now we've seen how to change the map viewpoint and to animate those to provide a nice, pleasing experience for the user. Thank you for watching our video on Android mapping.